Sampling is the bridge between analog RF signals and digital processing systems, but it only works correctly under strict mathematical conditions. If sampling is too slow, the signal becomes distorted and cannot be reconstructed. The Nyquist theorem defines the exact minimum sampling rate required to preserve all information. The Nyquist theorem states that a continuous time signal can be perfectly reconstructed from its samples if it is sampled at a rate that is at least twice its highest frequency component. This minimum rate is known as the Nyquist rate, and it forms a fundamental rule in digital signal processing and RF systems. This theorem is based on the idea that sampling converts continuous frequency content into discrete frequency representations. If the sampling rate is sufficiently high, each frequency component remains distinguishable and does not overlap with others in the sampled spectrum. The importance of this principle lies in ensuring that no information is lost during the conversion from analog to digital signals. It guarantees that the original waveform can be fully recovered from discrete samples without distortion. When a signal is sampled, it is effectively being measured at regular time intervals. If these intervals are too far apart, the system cannot capture rapid changes in the waveform, causing different signals to appear identical after sampling. The Nyquist limit defines the boundary between accurate representation and information loss. Below this limit, high-frequency components become indistinguishable from lower frequencies, leading to ambiguity in signal reconstruction. This intuitive view shows that sampling is not just about measurement, but about preserving frequency structure. The sampling rate must be high enough to capture the fastest oscillations in the signal. Aliasing occurs when the sampling rate is below the Nyquist rate. In this case, high-frequency signals are misinterpreted as lower-frequency components in the sampled data. This creates false frequency content that was not present in the original signal. This happens because discrete sampling cannot differentiate between different sinusoidal signals that align at sampling points. As a result, multiple continuous signals map to the same discrete sequence, causing irreversible information loss. Aliasing is one of the most critical problems in RF digital systems, and it must be prevented using proper sampling design and anti-aliasing filters before analog-to-digital conversion. In the frequency domain, sampling can be understood as a process that replicates the signal spectrum at multiples of the sampling frequency. If these replicated spectra overlap, aliasing occurs and signal information becomes corrupted. When the sampling rate is high enough, these spectral copies remain separated, allowing the original signal to be reconstructed perfectly using filtering techniques. This frequency domain interpretation provides a clear mathematical explanation of the Nyquist condition. This view is extremely important in RF engineering because it connects sampling behavior directly to spectral analysis, making system design more intuitive. The Nyquist theorem is fundamental in all digital RF systems, including communication receivers, software-defined radios, and radar processing systems. It determines how fast analog signals must be sampled to preserve all spectral information. In practice, RF engineers design ADC systems based on Nyquist criteria and often use anti-aliasing filters to remove unwanted high-frequency components before sampling. This ensures clean digital representation of analog signals. Without the Nyquist theorem, modern digital communication systems would not be able to reliably convert and process real-world RF signals. In this lesson, we learned that the Nyquist theorem defines the minimum sampling rate required to accurately represent and reconstruct a continuous time signal. We also saw how insufficient sampling leads to aliasing, causing different frequency components to become indistinguishable in the digital domain. In the next lesson, we will explore probability basics and learn how RF engineers mathematically describe uncertainty, randomness, and unpredictable system behavior. If you found this useful, like the video, subscribe, and follow for the next lesson.